The birth of the heliocentric theory, from Copernicus to the scientific revolution asterisk, in the history of human thought. There are turning points that not only transformed science, but also reshaped humanity's very perception of itself and the cosmos. One of these turning points was the heliocentric theory proposed by Nicolaus Copernicus. Emerging in the 16th century, at a time when the Catholic Church held intellectual dominance in science was bound by theological dogma, this theory was more than a scientific model. It became a symbol of the liberation of human reason. In De Revolutionibus Orbium Coelestium, Copernicus wrote, "In the middle of all sits the sun enthroned." In this most beautiful temple, could we place this luminary in any better position from which he can illuminate the whole at once? These words, poetic yet scientific, signaled a new worldview. The sun, not the earth, was the true center of the cosmos. Europe, before Copernicus, for over a millennium, the cosmological model of Claudius Ptolemy, 2nd century CE, had reigned supreme. According to the geocentric system, Earth stood fixed at the center, while the heavenly bodies revolved around it on concentric circles. To explain irregularities, such as retrograde motion, Ptolemy introduced complex epicycles, small circles riding on larger ones. Though mathematically ingenious, the system became increasingly cumbersome and unsatisfactory. The Catholic Church, aligning scripture with Ptolemaic astronomy, upheld the geocentric worldview as theological truth. Earth, and by extension humankind, was at the center of God's creation. Any challenge to this doctrine risked being branded as heresy. Yet, with the Renaissance revival of classical learning, mathematicians and astronomers began questioning the Ptolemaic system. Observations revealed discrepancies between predictions and actual celestial phenomena. Instead of a harmonious cosmos, the universe seemed a patched, fragile mechanism. It was within this intellectual tension that Copernicus entered the stage. Asterisk. The life of Copernicus and the formation of the heliocentric idea. Nicolaus Copernicus, 1473 to 1543, was born in Toru, Poland. Orphaned at a young age, he was raised by his uncle Lucas Watson-Rode, a bishop who ensured him a thorough education. Copernicus studied at the University of Krakow, later traveling to Italy to pursue law, medicine, theology, mathematics, and above all, astronomy. In Bologna, he befriended Domenico Maria Novara, a distinguished astronomer, and joined in observational studies. These experiences instilled in him doubts about the Ptolemaic model. He began to ask, if the cosmos is the handiwork of the Creator, why should its design be so convoluted? Around 1510, Copernicus drafted the Commentarius, where he first outlined his radical hypothesis. The sun rests at the center, while Earth and the other planets revolve around it. This simple shift unraveled the confusion. Retrograde motion of Mars, the brightness of Venus, and the order of the planets became intelligible. Copernicus later wrote, "If we assume the sun to be at the center, then all the apparent irregularities disappear. The planets no longer wander backward. It is the Earth's own motion that creates this illusion." Asterisk. The core of De Revolutionibus 4, more than 30 years of calculation and refinement. Copernicus completed his magnum opus, De Revolutionibus Orbium Coelestium, 1543. The work is divided into 6 books. Book 1 introduces the heliocentric model. Earth rotates on its axis and orbits the sun. Book 2 provides mathematical principles and trigonometric tables. Books 3v analyze the motions of the moon and planets within the heliocentric system. Book 6 explains the precession of the equinoxes and other long-term celestial changes. 1 pivotal passage declares, the Earth has 3 motions: rotation on its axis, annual revolution around the sun, and the inclination of its axis. These motions, though they seem complex, explain all observed phenomena of the heavens. Asterisk. although Copernicus still adhered to circular orbits, unlike Kepler later with ellipses. His model was vastly more coherent and elegant than Ptolemy's. Publication and reception. Copernicus hesitated for decades to publish his findings, fearing ecclesiastical opposition. Only under the encouragement of his student Georg Joachim Rheticus did he agree to print the work. De Revolutionibus was published in Nuremberg in 1543, the very year of Copernicus's death. Tradition holds that he glimpsed the first printed copy on his deathbed. To shield the book from immediate condemnation. Lutheran theologian Andreas Osiander inserted an unsigned preface, claiming the model was merely a computational hypothesis, not a description of reality. This rhetorical safeguard allowed the work to circulate among scholars without immediate prohibition. The initial reception was cautious. Mathematicians admired its precision, but many dismissed heliocentrism as a convenient fiction. Only with Galileo's telescopic observations and Kepler's laws of planetary motion in the 17th century did Copernicus's theory gain widespread acceptance. Historical, philosophical, and scientific significance. The heliocentric theory was not just an astronomical innovation. It marked a revolution in thought, the collapse of the medieval worldview. Humanity was dethroned from the cosmic center. Earth was merely one planet orbiting the sun, a small body in a vast universe. The dawn of scientific method. Copernicus relied on observation and mathematical reasoning rather than inherited dogma. His approach laid the groundwork for modern empirical science. Catalyst for the scientific revolution. Copernicus's model inspired the breakthroughs of Kepler, Galileo, and Newton. Newton himself remarked, "If I have seen further, it is by standing on the shoulders of giants." Copernicus was undoubtedly one of those giants. Philosophical and humanistic impact. By decentering Earth, Copernicus compelled humankind to adopt humility while affirming the right to seek truth independently of tradition. He birth of the heliocentric theory reflects the struggle between free inquiry and dogmatic constraint. Within the quiet life of a provincial canon and physician, Copernicus nurtured a seed of thought that would shape the foundations of medieval cosmology and inaugurate modern science. In De Revolutionibus, he wrote, "We seek not useless hypotheses, but the truth. Therefore we place the sun, as if on a royal throne, in the center, to govern the family of planets revolving around it." From that moment, humanity could no longer gaze at the heavens as before. Thanks to Copernicus, the universe was transformed from a theater of divine mystery into the object of science, reason, and unending exploration. From Tycho Brahe to Johannes Kepler, the road to the three laws of planetary motion. The scientific revolution was not merely a shift in knowledge, but a transformation in how humanity perceived the cosmos. After Copernicus introduced heliocentrism, European astronomy escaped the shackles of geocentrism. Yet the Copernican model was not perfect. He still adhered to circular orbits and epicycles to account for irregularities. To move further, two figures were indispensable. Tycho Brahe, 1546 to 1601, the Danish Nobel astronomer who produced the most precise pre-telescopic observational data, and Johannes Kepler, 1571 to 1630, the German mathematician and astronomer who transformed those records into the three laws of planetary motion. Tycho Brahe, life and intellectual context. Early life. Tycho Brahe was born in 1546 into a wealthy Danish noble family. Although destined for law, he became fascinated with the heavens at an early age. A solar eclipse in 1560, predicted with astonishing accuracy by astronomers, deeply impressed him and set him on a lifelong mission to measure the heavens. Education and early career. Tycho studied at Copenhagen, Leipzig, and Rostock, focusing on mathematics and astronomy. He became known for his passionate and fiery temperament, famously losing part of his nose in a duel, and thereafter wearing a metal prosthesis. The Uraniborg Observatory, with the patronage of King Frederick II. Tycho was granted the island of Hven to establish the Uraniborg Observatory in 1576. This became the most advanced astronomical center of its time, equipped with massive instruments capable of measurements accurate to 1 arcminute, an unprecedented achievement before the telescope. Major discoveries: the new star of 1572. Supernova. Tycho observed a new star in Cassiopeia, demonstrating that it lay beyond the moon, and thus disproving Aristotle's claim of celestial immutability. The comet of 1577. Through parallax measurements, Tycho showed that comets traveled through planetary space, undermining the belief in solid crystalline spheres. Precise astronomical tables. He recorded thousands of positions of the sun, moon, and planets, producing the most accurate database available for generations. Tycho Brahe's cosmological model. Tycho was unwilling to embrace Copernicus fully. Although he admired the mathematical elegance of heliocentrism, he found no observable evidence for Earth's motion. He therefore proposed the Tychonic system. The Earth remained stationary at the center. The sun revolved around the Earth. The other planets revolved around the sun. This compromise preserved both observational precision and religious political orthodoxy. Although later surpassed, it served as an important transitional model, allowing Copernican ideas to circulate more widely without provoking immediate rejection. Tycho and Kepler. A fateful encounter. In 1599, Tycho invited Johannes Kepler, a young German mathematician, to work with him in Prague. Kepler, a devout Copernican, lacked precise data. Tycho, conversely, possessed vast data but had not discovered a mathematical system to unify it. Their collaboration was tense. Tycho guarded his data jealously, while Kepler was impatient to analyze it. Fate intervened when Tycho died suddenly in 1601, leaving his enormous observational archive to Kepler. This inheritance marked a turning point for astronomy. Johannes Kepler and the quest for cosmic harmony. Background. Born in 1571, Kepler combined mathematical genius with deep religious devotion. He believed that the universe was constructed according to divine mathematical harmony, the language of God. Research on Mars. Kepler focused on Mars, a planet notorious for defying simple circular models. After years of laborious trial and error, he abandoned the age-old ideal of circular perfection and accepted the ugly truth. Mars's orbit was not circular but elliptical, the 3 laws of planetary motion. The first law, 1609, statement: planets move in elliptical orbits with the sun at one focus. Significance: for the first time, the perfect circle, long regarded as the divine form, was replaced by the ellipse. What had been seen as geometrically imperfect became the true shape of celestial paths. Publication: Astronomia Nova, 1609. The second law, 1609, statement: a line joining the sun and a planet sweeps out equal areas in equal times. Significance: planetary velocity is non-uniform, faster near the sun, slower farther away. This was a first step toward the modern concept of gravitational force. The third law, 1619, statement: the square of a planet's orbital period is proportional to the cube of its semi-major axis. T squared varies as A. Significance: this revealed a universal mathematical relationship among all planets. No longer was each planet an isolated case. All obeyed a common law. Publication: Harmonices Mundi, 1619. Significance and impact for science. Kepler transformed astronomy from descriptive geometry into a science of laws, preparing the ground for Newton's law of universal gravitation. For philosophy, Aristotle's vision of a perfect, immutable cosmos collapsed. The heavens were no longer separate, but governed by the same natural principles as Earth for religion and culture. Although deeply pious, Kepler saw his discoveries as a means of unveiling God's rational design. For humanity, Earth lost its privileged place as the cosmic center, becoming merely one planet among many in a vast and law-governed universe. If Copernicus lit the flame of revolution, Tycho Brahe provided the foundation of data, and Kepler converted that foundation into mathematical laws. Tycho once remarked, "Let others theorize. I will measure the heavens." Those measurements gave Kepler the chance to make his great leap. Kepler later confessed in Harmonices, "Monday, I feel carried away by unutterable rapture at the divine spectacle of heavenly harmony." From Tycho's eyes to Kepler's mind, humanity gained the three laws of planetary motion, the cornerstone for Newtonian mechanics and classical physics. This was the triumphant victory of reason in the scientific revolution. Johannes Kepler, 1571 to 1630, the scientist who consolidated and developed the heliocentric theory through the three laws of planetary motion when Copernicus published his De Revolutionibus Orbium Coelestium in 1543. He ignited an intellectual revolution. Earth was no longer the immovable center of the universe, but merely one of the planets orbiting the sun. Yet, his model still bore the marks of the old worldview, most notably the retention of circular orbits and epicycles to explain the irregularities of planetary motion. In the 17th century, Johannes Kepler, a German mathematician and astronomer, became the figure who consolidated and extended the heliocentric theory, drawing upon the unparalleled observational data left behind by Tycho Brahe. Kepler derived the three laws of planetary motion, transforming heliocentrism from a speculative hypothesis into a mathematically demonstrable and predictive scientific theory. The life of Johannes Kepler, early life and education. Johannes Kepler was born on December 27, 1571, in Wilderstadt, in the Duchy of Württemberg, modern-day Germany. Coming from a poor family, his childhood was marked by hardship and frailty. Despite chronic illness, Kepler revealed precocious talent in mathematics and an imagination captivated by the heavens. In 1589, he entered the University of Tübingen, where he studied both the Ptolemaic geocentric model and the Copernican heliocentric model. Under the influence of Michael Mestlin, one of the few professors willing to advocate Copernicus at the time, Kepler became an ardent supporter of the heliocentric worldview. Teaching career and early works, in 1594, Kepler was appointed as a mathematics teacher in Graz, Austria. During this period, he published Mysterium Cosmographicum 1596, in which he proposed that the spacing of the planets was determined by the 5 Platonic solids nested between their orbits. Though speculative and mystical in nature, the work revealed Kepler's lifelong quest to discover the mathematical harmony underlying the cosmos. Encounter with Tycho Brahe, an inheritance of data. In 1600, Kepler joined the research circle of Tycho Brahe in Prague. Tycho possessed the most accurate astronomical data in Europe, yet lacked the theoretical framework to explain it. After Tycho's death in 1601, Kepler was granted access to the entire trove of observations, most critically Tycho's detailed records of Mars. These data became the foundation for Kepler's epochal discoveries. The discovery of the three laws of planetary motion. The first law, elliptical orbits. Kepler spent years grappling with Tycho's precise measurements of Mars. No combination of circles or epicycles could fit the data. After exhaustive trial and error, he arrived at a radical solution. The orbit was not a perfect circle, but an ellipse. Statement: the planets move around the Sun in elliptical orbits, with the Sun located at one focus. Publication: Astronomia Nova, 1609. Significance: This shattered the classical conviction, rooted in Platonic and Aristotelian philosophy, that the circle was the perfect form of celestial motion. The second law, equal areas in equal times, analyzing variations in planetary speed, Kepler realized that Mars accelerated as it approached the Sun and slowed when farther away. Statement: a line joining the Sun and a planet sweeps out equal areas in equal times. Significance: this established that planetary motion is non-uniform, directly contradicting Aristotle's doctrine of uniform circular motion. The third law, harmonic, proportion in Harmonices Mundi, 1619. Kepler unveiled the third law, generalizing the relationship among all planetary orbits. Statement: the square of a planet's orbital period is proportional to the cube of the semi-major axis of its orbit. T squared varies as A. Significance: for the first time, a single mathematical formula linked orbital distance with orbital time, revealing the Sun's gravitational harmony as the unifying principle of the solar system. Kepler and the consolidation of heliocentrism. From philosophical hypothesis to mathematical law, Copernicus's heliocentrism remained a largely philosophical conjecture, lacking rigorous evidence. By grounding the system in three mathematically exact laws, Kepler transformed heliocentrism into a predictive scientific framework, capable of calculating planetary positions with precision. Refutation of geocentrism and geoheliocentrism. Kepler's laws eliminated not only Ptolemy's geocentrism, but also Tycho's compromise system of a geoheliocentric model. The elliptical orbits placed the Sun unequivocally at the dynamical center, relegating Earth to one among many moving planets. Laying the groundwork for Newton, Kepler's laws not only vindicated Copernicus, but also paved the way for Newton. By analyzing Kepler's formulations, Newton derived the law of universal gravitation, explaining why the planets moved as they did. Kepler had given the what, Newton supplied the why. The broader significance of Kepler's laws' impact on science. They ended the era of speculative cosmology rooted in Aristotelian metaphysics. They inaugurated modern astronomy, where celestial motion was governed by mathematical law rather than philosophical assumption. Philosophical and intellectual implications. They undermined the notion of a perfect, immutable cosmos. They affirmed that the universe was intelligible through human reason and mathematics. Religious and cultural meaning. Kepler remained a devout Christian, interpreting his discoveries as glimpses into the divine order. In Harmonices Mundi, he described planetary orbits as part of a celestial symphony, a harmony composed by God himself. For humanity's self-understanding, Kepler's work displaced Earth from its privileged centrality, situating it as one planet among many. Yet, in doing so, he empowered humanity with the intellectual capacity to comprehend the cosmos, a humbling but ennobling achievement. Conclusion: Johannes. Kepler elevated heliocentrism from conjecture to law. Through the three laws of planetary motion, he supplied the empirical and mathematical foundations that Copernicus lacked, dismantled the millennia-old notion of uniform circular motion, prepared the conceptual ground for Newtonian mechanics and universal gravitation. Kepler wrote in Harmonices Mundi, "I feel carried away by an unutterable rapture at the divine spectacle of the heavenly harmony." This was not merely the declaration of a scientist, but the hymn of a soul who united science, religion, and art into a vision of cosmic order. Through Kepler, the heliocentric theory matured into a cornerstone of the scientific revolution, forever altering humanity's conception of its place in the universe. Isaac Newton and the law of universal gravitation, the culmination of the scientific revolution. The 17th century was an age of intellectual upheaval and transformation, an age historians would later call the scientific revolution. From Copernicus's daring heliocentric hypothesis to Kepler's meticulous planetary laws and Galileo's telescopic revelations, the foundations of natural philosophy were shifting. Yet, It was not until Sir Isaac Newton, 1642 to 1727, the English mathematician, physicist, and natural philosopher, that these scattered discoveries were unified into a single, coherent system of natural law. Newton's formulation of the law of universal gravitation and his three laws of motion did more than explain the mechanics of the heavens and the earth. They reshaped humanity's conception of the universe itself. No longer was the cosmos a realm divided between celestial perfection and terrestrial imperfection. Instead, it was governed by the same universal principles, subject to the same immutable laws. This essay explores the life of Newton, the intellectual context in which he worked, the development of his gravitational theory, and the profound impact of his discoveries on science and philosophy. Newton's early life and education. Isaac Newton was born on December 25, 1642, January 4, 1643, in the modern calendar, in Woolsthorpe, Lincolnshire, England, the same year that Galileo Galilei passed away. Born prematurely and described as small and frail, few expected the infant to survive. Newton's father, a yeoman farmer, had died before Isaac's birth, and his mother soon remarried, leaving him in the care of his grandmother. This difficult childhood shaped Newton's solitary and intensely introspective personality. Newton attended the King's School in Grantham, where his brilliance in mechanics and mathematics soon became apparent. He built sundials, windmills, and even a miniature water clock. In 1661, he entered Trinity College, Cambridge, where he encountered the works of classical authorities like Aristotle, as well as the revolutionary ideas of Descartes, Galileo, and Kepler. Cambridge was then undergoing a transformation, with new currents of mechanical philosophy challenging scholastic traditions. Newton absorbed these ideas eagerly, while also pursuing his own investigations in mathematics, optics, and natural philosophy. The Annus Mirabilis, 1665-1666, the years 1665 and 1666, when Cambridge closed due to the Great Plague, proved to be Newton's most creative period. Retreating to Woolsthorpe, Newton worked in isolation. Yet it was in this solitude that he laid the groundwork for his most enduring contributions. During this time, Newton invented calculus independently of Leibniz, who developed his own notation a few years later, began his optical experiments, leading to his discovery that white light is composed of the spectrum of colors, formulated the beginnings of his gravitational theory, inspired, according to later accounts, by observing an apple fall in his orchard. The story of the apple, though embellished, symbolizes Newton's genius, the ability to connect everyday phenomena with cosmic order. If an apple falls to the ground, might the same force extend outward, reaching as far as the moon, keeping it in orbit around the Earth? The intellectual context, from Copernicus to Kepler, Newton's theory of universal gravitation did not emerge in a vacuum. It was the culmination of more than a century of astronomical and physical inquiry. Copernicus, 1473 to 1543, had displaced the Earth from the center of the cosmos, proposing a heliocentric system. Yet his model still relied on circular orbits and epicycles, making it mathematically complex. Tycho Brahe, 1546 to 1601, provided precise astronomical observations, compiling data on planetary positions that far surpassed any before him. Johannes Kepler, 1571 to 1630, using Tycho's data, discovered his three laws of planetary motion: elliptical orbits, equal areas in equal times, and the harmonic relation between orbital period and distance from the Sun. These laws were empirical, but lacked a unifying physical explanation. Galileo Galilei, 1564 to 1642, established the principle of inertia, studied falling bodies, and confirmed the Copernican system through telescopic observations by Newton's time. The question remained, what physical force could explain Kepler's mathematical laws? How could Galileo's mechanics be reconciled with Kepler's celestial harmonies? Newton's laws of motion. Before addressing gravity, Newton codified the basic principles of motion in his three famous laws. Law of inertia. Every object continues in its state of rest or uniform motion in a straight line unless acted upon by an external force. Law of acceleration. The change of motion is proportional to the applied force and occurs in the direction of the force, F equals ma. Law of action and reaction. For every action, there is an equal and opposite reaction. These laws generalized and extended Galileo's insights, providing a mathematical framework to describe motion both on Earth and in the heavens. The law of universal gravitation. Newton's crowning achievement was his formulation of the law of universal gravitation, first fully expressed in his monumental work Philosophiae Naturalis Principia Mathematica, 1687, often referred to simply as the Principia. The law states, every particle of matter in the universe attracts every other particle with a force that is directly proportional to the product of their masses, and inversely proportional to the square of the distance between them. Mathematically, this law unified the terrestrial and celestial realms. The same force that pulls an apple toward the ground also keeps the moon in orbit around the Earth, the planets around the sun, and governs the tides of the seas. The Principia, 1687. Newton's Principia is arguably the most important scientific book ever written. Structured in 3 books, it lays out his laws of motion, the mathematical principles of mechanics, and the universal law of gravitation. Book I deals with the mathematical foundations of motion and the properties of bodies under central forces. Book II addresses fluid dynamics and the motion of bodies in resisting mediums. Book III applies the principles to the cosmos, demonstrating how the law of gravitation explains Kepler's laws of planetary motion. In the Principia, Newton famously declared, "I have not as yet been able to discover the cause of these properties of gravity from phenomena, and I frame no hypotheses." This statement, hypotheses non fingo, I feign no hypotheses, became emblematic of Newton's scientific method. He derived laws strictly from observation and mathematical reasoning, without speculating about underlying causes. The impact of the law of universal gravitation. The implications of Newton's gravitational law were vast and revolutionary. Unification of the heavens and earth. No longer were celestial motions governed by divine or mystical principles. The same laws applied universally. Confirmation of heliocentrism. Kepler's laws, once descriptive, were now explained by a universal force emanating from the sun. Predictive power. Newton's laws allowed for precise predictions of planetary orbits, eclipses, and the motion of comets. Halley's comet, for instance, was successfully predicted by Newton's contemporary, Edmund Halley, using Newtonian principles. Influence on philosophy. Newton's universe was mechanistic, orderly, and comprehensible, influencing Enlightenment thinkers like Voltaire, Locke, and Kant. Opposition and legacy. While Newton's ideas were rapidly embraced, they also faced resistance. Some critics questioned the notion of action at a distance. How could gravity operate across empty space without a medium? This objection would not be fully addressed until Einstein's theory of general relativity in the 20th century. Nevertheless, Newton's gravitational theory became the cornerstone of classical physics, dominating scientific thought for over 2 centuries. His synthesis represented the triumph of reason and mathematics, the epitome of the scientific revolution. Isaac Newton's law of universal gravitation was not merely a scientific discovery. It was a paradigm shift that transformed humanity's view of the cosmos. By uniting the work of Copernicus, Kepler, and Galileo into a coherent framework, Newton provided the foundation for modern physics and astronomy. His insights marked the culmination of the scientific revolution, opening the path to the Enlightenment and to the scientific advances that followed. As Alexander Pope famously wrote in his epitaph for Newton, "Nature and nature's laws lay hid in night. God said, 'Let Newton be,' and all was light." Through Newton, the universe became intelligible, governed not by mysteries or divine caprice, but by universal laws accessible to human reason. His legacy endures, a testament to the power of the human mind to comprehend the cosmos.